12.3 Newton's third law of motion and momentum. Think physics the next time you go to the amusement park. There is no better place than an amusement park to see Newton's laws in action. As you experience sudden stops, starts, and changes in direction, and possibly even freefall, you can be sure that the laws of physics control your motion. The bumper cars in Figure 15 illustrate momentum and Newton's third law of motion, the subjects of this section. If you have ever driven a bumper car, you know your goal is to slam into another car head on. When you collide with the car, you do so with enough force to jolt the other driver almost out of the seat. There are two parts to this collision. However, the collision also causes your own car to rebound sharply. Newton's third law of motion explains the behavior of the bumper cars during a collision. Newton's third law. A force cannot exist alone. Forces always exist in pairs. According to Newton's third law of motion, whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first object. These two forces are called action and reaction forces. The force your bumper car exerts on the other car is an action force. The force of the other car exerts on your car is the reaction force. These two forces are equal in size and opposite in direction. Pressing your hand against a wall also produces a pair of forces. As you press against the wall, your hand exerts a force on the wall. This is the action force. The wall exerts an equal and opposite force against your hand. This is a reaction force. A similar situation when you use the hammer to drive a nail into a piece of wood. When the hammer strikes the nail, it applies a force to the nail. The action force drives the nail into the piece of wood. Is there a reaction force? According to Newton's third law, there must be an equal and opposite reaction. The nail supplies the reaction force by exerting an equal and opposite force on the hammer. It is this reaction force that brings the motion of the hammer to a stop. Action-reaction forces in motion. Can you determine the action and reaction forces occurring in Figure 16? The swimmer uses his arms to push against the water and create an action force. The action force causes the water to move in the direction of the action force. However, the water also exerts its equal and opposite reaction force on the swimmer. The reaction force acts on the swimmer and pushes her forward through the water. Unlike the swimmer in Figure 16, not all action and reaction forces produce motion. Pushing against the wall with your hands is an example of an action-reaction force pair that does not result in motion. Action-reaction forces do not cancel. You may be wondering why the action and reaction forces acting on the swimmer in Figure 16 do not cancel each other and produce a net force of zero. The reason is the action and reaction forces do not act on the same object. The action force acts on the water, and the reaction force acts on the swimmer. Only when equal and opposite forces act on the same object do they result in a net force of zero. Momentum. Imagine a loaded shopping cart and a small glass marble are both slowly rolling toward you at the same speed. The marble is easy to stop. Intuitively, you know that a loaded shopping cart is harder to stop because it has greater mass. If the marble were moving 100 times faster than the shopping cart, which would be easier to stop? Momentum is the product of the object's mass and its velocity. Mass times velocity. An object with larger momentum is harder to stop. An object has a large momentum if the product of its mass and velocity is large. The momentum for any object at rest is zero. A huge rocket such as the space shuttle has zero momentum as it sits on a launch pad. Think about that. It's very heavy, but going 0 miles per hour. Anything times zero is zero. So therefore, an object that is not moving has zero momentum. You can calculate momentum by multiplying an object's mass and its velocity. The momentum formula is mass times velocity, as you see up here on page 375. Momentum is measured in the units of kilograms per meters per second. So which has more momentum? A 0.046 kilogram golf ball with a speed of 60 meters per second, or a 7 kilogram bowling ball with a speed of 6 meters per second? Well, when you do the math out, you clearly see that the bowling ball has greater momentum, even though it's traveling at a much lesser speed. So basically, all we're doing, we're going to let the math speak for itself. Mass times velocity gives us the momentum. The bowling ball has considerably more momentum than the golf ball in this case. Conservation of momentum. What happens to the momentum when objects collide? Look at the collisions in Figure 17. Under certain conditions, collisions obey the law of conservation of momentum. In physics, the word conservation means that something has a constant value. That is, conservation of momentum means that momentum does not increase or decrease. Imagine two trains colliding, as shown in Figure 17a. If the two cars are part of a closed system, the momentum is conserved. A closed system means the objects and forces cannot enter or leave a system. Objects within the system, however, can exert forces on one another. According to the law of conservation of momentum, if no net force acts on a system, then the total momentum of the system does not change. Thus, if we consider the two train cars as a closed system, the cars can exert forces on each other. In a closed system, the loss of momentum of one object equals the gain of momentum of another object. Three different closed systems are shown in Figure 17. Each system consists of two trains with the same mass that collide. In Figures 17a and b, the trains collide and then bounce apart. In Figure 17c, the cars collide, then join together. Examine the momentum of each car before and after collisions. Note that the total momentum before and after each collision does not change. The momentum is conserved. 12.3 assessment questions. 1. Using Newton's third law, explain what is meant by action and reaction pairs of forces. 2. State in your own words the formula for momentum. 3. What is a necessary condition for the conservation of momentum? And 4. If an eagle and a bumblebee are traveling at 8 kilometers per hour, which has more momentum? Explain. This concludes 12.3, Newton's third law and momentum.